Hello there, welcome to my channel on chemistry lessons. This is an A-level chemistry lesson and it's the very beginning of organic in year 12 and it's the introduction to organic. First up though, if you don't subscribe, please do. Your support is very much appreciated and please take advantage of the likes and comment features. Let me know what we think. So this section involves us requiring some prior knowledge. So I'm going to go through some key points that we should already be aware of. So an organic compound or molecule is a carbon-based molecule, so it contains mostly carbon atoms. But it will contain other elements such as hydrogen, oxygen, nitrogen, and sometimes you'll find some halogens in there, which are elements from group 7, such as bromine, fluorine, chlorine. Carbon will always have 4 covalent bonds, so every time we draw an organic molecule, carbon will have 4 bonds. Hydrogen will always have 1 bond. Oxygen will always have 2 bonds. Nitrogen will have 3, but I'm not putting that in the list here because we're not too concerned. We're not going to come across too many nitrogen-based compounds. Halogens will always have 1 covalent bond. Now I've underlined this one because I am going to cover this topic here. So we're going to look at organic molecules being called homologous series. So we're going to look at what a homologous series is, but it basically means that they have different functional groups. They can be put into different groups based upon characteristics in that molecule. We can also classify them as aliphatic, alicyclic, and aromatic. I'm going to define some of those terms here because they will be new. An aliphatic means that the molecule is joined together in a straight or a branched chain. So we're going to see straight chain aliphatic and we're going to look at some branched chain aliphatic today. Alicyclic means that it's in a ring structure. It's a cyclic, and we'll see some examples of those today, hence I've underlined it. An isomer, as I've said earlier, we will look at the introduction to isomers, but we will look in more detail on a further video. But an isomer is a molecule that has the same molecular formula, so that means the same number and types of atoms, but they are arranged differently, so they are bonded together in different orders. And the term aromatic means it contains at least 1 benzene ring. Now that means nothing at the moment, and again that's going to be covered in other videos. So let's look at what we mean by a homologous series. You're probably already aware of 2 homologous series from GCSE or from previous units, but 2 homologous series are alkanes and alkenes. And why are they classed as homologous series? Well, that's because they have the same general formula, they have the same functional group, they have similar chemical properties, they show trends in physical properties, and the members in the group differ by a CH2 group. Let's look at some examples of some straight chain aliphatic then. So the top one is a straight chain aliphatic alkane. I know it's an alkane because it only contains carbon-carbon single bonds, and if you were to count that, you'll recognise that it matches the general formula. So we've got C4, we've got 4 carbons, and if you count the hydrogens, we have 10. So it matches the general formula. 2 times 4 is 8 plus 2 is 10. So it matches the CnH2n plus 2. That's classed as saturated because it only contains single bonds. The one underneath is an aliphatic alkene. And again, if we were to count the number of carbons, there are 4. And if you count the hydrogens, you will find there's 8. And it matches the general formula CnH2n. Now, why are they classed as straight chain? That's because the carbon atoms are bonded end on end to each other. So it's a straight chain. The carbons are in a straight chain. Doesn't necessarily have to be a straight line. It just means that they're bonded to each other one after the other. So each carbon is bonded to 2 other carbons, apart from the carbon on the end is only bonded to 1. You could also spend some time counting the number of covalent bonds. Every carbon has 4 covalent bonds. and every hydrogen has one covalent bond. I will take the opportunity to point out that the molecule on the bottom, the alkene, what we could do is we could move that double bond to a different position. So I could move the double bond here, which would require me removing this hydrogen, and I'd have to remove this double bond here. That's still classed as an aliphatic alkene, but I've moved the double bond to a different position. So it's possible in that example there that the double bond could be between the second and third carbon, or it could be at the end of the chain. And that's an early example of an isomer, because it still has the same number and type of atoms, but they're bonded together in a different way. It's got a different structure. So now let's look at a couple of examples of aliphatic branched. So what we can see here is on the top one, the alkane, it's not a straight chain. So the carbons don't just go in one straight chain. We've got the same number of carbons here, so we still have 4 carbons. And if we count the hydrogens, you'll find that you've still got 10. So it still has the same formula as the straight chain C4H10. But this one is classed as branched because we have a chain and then a side, or we call a branch. So there's a branch on this alkane. So this is a branched aliphatic alkane. But it does have the same formula as the straight chain with 4. So again, we can see that as an example of isomerism, because they both were C4H10, but they have different structures. So same molecular formula, but different structure. And very similarly with the one underneath, the alkene, again, we've got 4 carbons. And if you count the hydrogen, you'll find that it has 8, which is identical to the alkene on the previous slide. However, again, this is now a branched alkene because we have 3 carbons in a chain and we have a branch. So this is classed as an aliphatic branched alkene. And again, that would be an isomer of the alkene on the previous page. So branched chain and straight chain have isomers. They can be isomers of each other because they have the same molecular formula but a different structure. So the final structure type we're going to look at is alicyclic. Now these look very odd to start with, so you may wish to pause the video and take a little look at what's going on, but you will find that each carbon has 4 covalent bonds and each hydrogen has 1. But they form a cycle, so it's like a cyclic group. Now what's interesting about these is if we look at the alkane, so the top one, the top left is classed as an alicyclic alkane because there's only carbon-carbon single bonds. If you count the carbons here, you'll find that we've got 6. And if you count the hydrogens, you'll find there are 12. Now, that does not match the general formula of the alkanes because Cn, so if we times 6 by 2, that's 12, and then add 2 is 14. So we would expect it to be C6H14 for an alkane, but in fact it's not. Even more interestingly, it actually matches the formula for an alkene. So we have a different type of isomerism here. You'll see that alicyclic alkanes are isomers of alkenes because we could draw C6H12 as a straight chain alkene. We could even draw it as a branched alkene. So C6H12 is classed as a functional group isomer because it could be a alicyclic alkane or it could be a straight chain or branched alkene. If we look at the bottom right, that's classed as an alicyclic alkene. Again, if you count all the bonds, you'll find carbon has 4, hydrogen has 1. And this doesn't match the general formula for the alkene either. We've got C6, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it doesn't match the general formula of an alkene, but that's classed as alicyclic groups. So just to summarize what we found with isomers then. So we've got straight chain, can be isomers with some branched chains because they can have the same molecular formula but different structures. We've also seen that alicyclic alkanes are functional group isomers with alkenes because they had the same formula but different structures. And that's the end of those kind of early fundamentals that we need to be aware of for organic. So hopefully that was useful, and please look out for the other videos that will follow on from this one. Thanks again.